Our next part is binding energy for a nucleon versus atomic mass graph. This is very important in explaining and understanding the nuclear reactions happening, like fusion and fission. So when the binding energy for nucleon versus the atomic mass is plotted, the graph is something like this. So starting from the lowest atomic number, like hydrogen, and there's helium, and it goes up to iron and lead. And this part you can see the uranium, thoriums, like stuff. U-238. So basically, the higher the atomic mass, the graph will go like this. It will first pick up and then slowly reduce to a specific value. Now, as you can see from this graph, that every element tries to achieve stability by either emitting or absorbing. So it's easier to understand that these are the lighter nucleus. They're trying to achieve a stability here. So basically, stability. And these heavy nucleus is trying to achieve stability here. Because this is the stable most portion. Binding energy for nucleon is the highest. So maximum energy will be required to separate a nucleon from the nucleus. This explains why the lighter nucleus like hydrogen, helium, lighter nuclei tends to fusion. They will join and form a heavy nuclei trying to attain stability. And this heavier nuclei tends to fission. They will break, form a smaller nuclei with lower atomic number, and they will try to achieve stability. There are certain peaks in the graph where the stability is more than expected. We are expecting the stability to be here, but it's actually here. These are not properly explained by science yet, and these are called magic nuclei. And the N and Z in case of these magic nuclei are like 2, 8, 28, 50, like that. And when both of these N and Z, they are both magic numbers, this is called a doubly magic nuclei. There are more magic numbers. Actually, it's like 82, 126, like that. So basically, for Z greater than 100 or equal to 100, these are termed as super heavy nuclei. And lead is one of it. If we see lead, it's basically 82, 126, and 200. So what do we see? N is 82, Z is 126. Both are magic numbers. So this is a doubly magic nuclei. And that's why lead is so stable. Because we can see that the lead is in one of the peaks of this graph, as I was saying here, the magic numbers. And most of the radioactive elements that are in nature, after decaying, they try to attain stability by becoming either lead or ferrous, that's iron. So this is one of the major reasons that iron is so much abundant in the nature, because all the elements that's radioactive, that's emitting, or any other elements that's not stable, that's trying to gain stability, and lead has the highest stability. So basically everyone, lead and iron, so basically everyone is trying to be either lead or iron. Now why exactly the graph is like this? A nucleus has two forces between the neutron and proton, between the proton and proton, and between the nucleons. So basically, one is the attraction force or strong nuclear force. It's very short ranged, and the another is Coulomb repulsion, relatively longer range. This is between the light nuclei, like protons. So, in this graph, basically, when the nuclei number is less, smaller nuclei number, so neutron by proton ratio is close to 1, like in carbon. So for one neutron, you have one proton. What happens is, there are protons, if they are close enough, they will be repelled. But if there is one neutron or multiple neutrons in between, there will be strong nuclear forces in between. So basically the repulsion is nullified by the strong nuclear force between neutron proton, neutron proton. So with increasing the neutron number, the stability increases. With increasing atomic mass, the stability will increase, because there are more neutrons per proton to stabilize the Coulomb repulsion. Whereas you can say that this part has far higher neutrons per protons than this part. Still, why the stability is reducing? Well, it's expressed by the term, by the form, that the protons in this part are significantly higher as well, so they have higher enhanced nuclear repulsion, Coulomb repulsion. Plus, with increasing neutrons, there are, we can see, more neutrons compared to these lead and iron, where the stability is achievable. So basically there are excess neutrons than required, and that's attributes to the slightly reduced stability here, and there are more neutrons, as I am saying. This is the reason why these parts are radioactive. These elements in this part of the graph are generally radioactive, like uranium, thorium, plutonium. So this increasing